we have seen the ideal characteristics graph of drain current with respect to drain to source voltage and gate to source voltage. But practically it has been observed that the graph is not as simple as it seems. Like we have seen, when the gate to source voltage is smaller than threshold voltage, then there should not be any current. Similarly, we have also seen that when drain to source voltage is greater than overdrive voltage, then the current should become constant. But none of these things happen in practical case. In this and the next lecture, we will see non-ideal effects which results in the deviation of ideal characteristics of a MOSFET. The first is the channel length modulation, which we have discussed already. The thing is, the channel length modulation occurs predominantly in enhancement MOSFET only. That's why we have already discussed it when we were discussing the characteristics of enhancement MOSFET. For your reference, the link is already provided at the top. Our next non-ideal effect is body biasing effect. We know MOSFET has actually 4 terminals, but after shorting source and body terminal, we are left with effectively 3 terminals only. But it is not necessary that body and source terminals are shorted always. Whenever there is a potential difference between body and source terminal, then there will be a change in threshold voltage. This effect is referred as body biasing effect. In the unit of MOS capacitor, we have derived the value of threshold voltage in terms of surface potential and capacitance per unit area. Here in this formula, we have assumed body and source terminal are shorted. Now, from this formula only, we can find the value of threshold voltage when there is a potential drop between source to body. In this formula, we have assumed all the potential difference between the source and body drops within the semiconductor. In the MOS capacitor, we have discussed the external applied voltage drops only in oxide and semiconductor, and there is no potential drop within the metal. But here we are assuming all the potential is dropping within the semiconductor only. The potential drop does not occur neither in oxide nor in metal. Let's name this equation. Now, subtracting equation 1 from equation 2, we will have the value of threshold voltage at any voltage difference between source to body will be equal to threshold voltage when source and body terminals are shorted plus gamma multiplied by under root of surface potential plus potential difference between source to body minus under root of surface potential, where gamma is referred as body coefficient, which is equal to under root of 2 times of magnitude of charge on an electron multiplied by doping concentration into permittivity of the semiconductor divided by capacitance per unit area. We also know surface potential is equal to 2 times of Fermi potential at threshold voltage. So we can also modify the formula to get threshold voltage in terms of Fermi potential. Except channel length modulation, all the other non-ideal effects like body biasing effect and the ones which we are going to discuss next occurs in both enhancement and depletion type MOSFET. Our next non-ideal effect is subthreshold conduction. We have assumed when the gate to source voltage is smaller than threshold voltage, then there will be no current flowing inside the MOSFET. But practically, the situation is quite different. Actually, there is a current which flows within the MOSFET even when the gate to source voltage is smaller than threshold voltage, but the magnitude of this current is very small. The current when gate to source voltage is smaller than threshold voltage is referred as subthreshold current, and the corresponding region in the transfer characteristics graph is sometimes referred as subthreshold region. Drain current in subthreshold region is directly proportional to the exponential of gate to source voltage. From the shown relation, we can say whether we increase gate to source voltage or drain to source voltage, the drain current in the subthreshold region will increase in both the cases.